The second submittal that I have is going to be for the column design. You guys know the column size in this project? Anyone recalls?
16 by 16.
Yeah, it says right here. Right? Now, which column do you think is going to have the highest column load? Can you mention it by grid line? You say intersection of grid line, something and something, right? Which one do you think?
B2.
2 and what?
B.
2 and B. Okay.
Yes.
See, this give you the column. How much is the tributary area that this column supports? How much is this distance from here to there?
26.
26 feet. Okay. And this dimension from here to there is how much?
28.
28 feet. So I guess you know tributary area is going to be 26 by 28. And how many levels we have in this project?
5? No, 4.
It says here.
4.
All right. So you need to figure out the total load. How do you do this? You do dead load for the roof and live load for the roof. Dead load for the second or for the third and then for the second. And then you add them up. At the end, you're going to have this P ultimate on the column. How do you do it? At the end of the day, you need to have 1.4 dead versus 1.2 dead plus 1.6 live load. And then at this point, you say, this is going to be the design load for the column. And this is going to be under this piece here. So when it says here service, it means that you need to have it as dead load separate from live load. At the bottom, right above the footing. And then you need to find out P sub U, which is the ultimate. It says here, pick the column that's exposed to the largest vertical load, and I guess you have just done it. You say it's going to be this grid line, right? Which is the same as this, same as this, same as this. But I don't want you to go to an edge column or corner column and then design it. No, I didn't ask for this. Just ask here for the column with the biggest load. It says here now, you have the column dimensions, and the other question is going to be about the material properties. What concrete strength do you think I need to use here? Do we have it? Is it written here somewhere? Oh, it says 4,000. You see this? Gravity columns. Good. So you're going to be taking 4,000, take the concrete, the column size 16 by 16, and then it says here, use the column size and concrete strength as indicated in the project statement to design the column vertical reinforcement. Now you need to design the vertical reinforcement. And don't forget that also you have a range. It needs to go between 1% and 8%. So I guess you're going to start with the lowest value, with the 1%, and then see if you have enough capacity. And then after that, you design the column tie reinforcement. How do you design here the column tie reinforcement? We have certain limits for the spacing. You need to go through it, and you can go, let's say it was number 4, right? Or number 3 if you want to, but number 4 is okay, and then figure out the spacing. And don't forget that this project is in California, which means maximum spacing is going to be limited to additional item, which is 6 inches. Any questions on the submittal? These two submittals should be very small, especially for the column one. It's going to take very limited time. I mean, this is very simple. Also due to the shear design that I don't see here an issue with it. So, any questions on submittals?
Yes. We designed for all 4 levels or just?
You design one section all the way at the bottom.
Okay. Thank you.
Meaning?
Any specific slide you recommend us looking at for this submittal?
Good question. So can you help me, please? If you can go back to the presentation and tell me how many column slide set that we have in there. I don't know what you guys have. How many column slide sets?
2.
2. What do you have in the first one? Can you help me, please, with this? What's the first one about? What is the second one about?
Give me a second.
So number 9, which was what we discussed last week,
Mine is a little
is
slow, so it's
we
loading.
discussed tied
Okay.
and spiral.
Oh, so number 10 is about spiral, number 9 about tight columns. How about this project? Do we have tight column or spiral column?
Tight.
Okay, good. So what slide set I need to be looking at here?
Number 9.
Okay, good. I just opened it. I
9.
was looking for it. So, okay, this is giving you the slide set that you need to look at. And the good thing is recorded. So if you miss any of that, you can just go back and look at it, okay?
Okay, thank
I'm
you.
just thinking here, no problem. I'm thinking here if I'm gonna be taking here this, like 4 stories, right? I'm gonna say, here we go. Now I have 1, 2, 3, 4. I have a roof. What would you call this? This is gonna be first, second, third, fourth, and then a roof. So you have 1, 2, 3 slabs. They're gonna be identical, and the roof is gonna be slightly different. When you design the column at this point, right here. So you need to find out the load coming from the roof, fourth, third, and second. Just add them up all together. At the end here, you're gonna have P dead load and P life load. So I'm gonna write them here. This is gonna be P dead load and P life load and then P ultimate. How do you do this? You say it's gonna be equal 1.4 P dead load versus PU equals 1.2 P dead load plus 1.6 P life load. You see which one is gonna be higher in value and just use it in your design. Questions? All right. Now let's continue here with today's lecture, which is about spiral column. I guess we know the difference between tight column now and spiral column. Spiral column going to show higher performance because of spiral, because you're containing here all the concrete. And once you contain it, we say that you provide lots of pressure in the surrounding of this concrete column. And this is going to help in the axial load capacity. So here's the axial load, and this is going to be helping out. This lateral restraint. We call this confinement, meaning that here you provide more confinement than what you provided here. And this confinement is going to increase or enhance the concrete properties. Here's some pictures. I mean, you have seen this before in the previous slide set. Same thing. You're going to have one continuous spiral in this case. And guess what? This is going to be the difference in performance between a spiral column, when you provide here lots of confinement, versus just tight columns with less confinement. Let's look here at the concrete stress-strain relationship. So this is going to be a relation between the stress that you apply to the concrete versus the amount of strain, vertical strain. This curve here is going to be for the unconfined, from here to there, right? So it's going to be this one. You start to apply pressure, the concrete is going to show here some strain, right? And this is going to reach to the max, the peak, which is F prime C. And then after that, the concrete here is failing. Now the concrete is gone. The maximum strain that usually this conventional concrete or unconfined concrete is going to be 0.04. Code says, SI code says we're going to consider it only 0.03. And we hear about this before. This is not the first time. In reality, when you apply here this amount of confinement, the strength of the concrete itself is getting large. I mean, it's going to be much higher. You're going to have maybe about 15%. See what happened here? If I may look for what happened in terms of the performance of the concrete. Right at this point, you see what happened? The confined concrete property is going to start to go up. You see this here, F prime CC? F prime C is going to be for concrete, CC for confined concrete. And it says here confined concrete. You see here the trend is going higher, and this is about maybe 10 to 15% at least. But look at the big difference here. Big difference is going to happen in the amount of strain capacity. Here, we're able to reach 0.04. But with the confinement, we're able to reach 0.09. Maybe 0.08. Depends on the amount of confinement. This kind of typical or standard stress-strain relationship. It doesn't mean that the code here is going to tell you when you have confined concrete, take concrete strain up to 0.09 or 0.08. No. The code would say concrete is going to be failing is still at 0.03. So this is going to be here the code value. So let me write this down. Code value. Meaning, code is not going to change the statement that the maximum strain in the concrete or the attainable strain is going to be 0.03. He's not going to change this because now you provide confinement. But he's going to acknowledge this issue. This he recognized. Meaning, for confined concrete columns, like the spiral columns, you're going to have higher factors when it comes to the strength of the column. Now, this is going to make me here open this slide set, which is for tight columns, and just quickly here go through the strength equation for the column. Here's the equation. If you recall, we said that we have here a few factors. The first two factors that we were talking about, the first one says account for small eccentricity, because usually you're going to have some eccentricity on the column anyways. So we're going to reduce here to 0.8. And look at this value here. Phi factor is 0.65. But when you go here to the code phi factor, you see for a spiral, you have it as 0.75. So actually the code understands that spiral columns is going to be stronger because you provide here more confinement. And the concrete properties is going to get enhanced. But the code doesn't say, go ahead and use higher strain value, but instead they give you higher value for this phi factor. So phi factor here becomes 0.75 and it's 2.65 for tight columns. Are we good about this? Yes? No? Okay. Can I ask questions? Let me choose people. All right. Blake. Are you there? Blake?
Yeah, sorry, I'm here, Professor.
You're there. Okay. Just quick question here. Would the code include any language about allowable maximum strain in the concrete to be 0.07, for example, or higher when it comes to confined concrete?
Yeah.
So the code says, if you provide here confinement, similar to what you do, let's say in a spiral column, it's okay when you do your design equations that we're going to be letting you to use 0.07 or more when it comes to the maximum allowable strains. Am I correct?
Yeah, right.
This is correct?
I believe so.
Okay. Okay, Angel, can you answer this question, please?
Sure.
Is this true that the code is going to let you use a strain higher than 0.07 or 0.06?
It's gonna depend on your design, right? If it's tight, obviously you're not gonna have as much confinement, but the more tightly wound, I guess, your spiral, the more confined your concrete is.
Okay, so the code says that it's okay if you have confinement to use 0.06 or 0.07.
Yeah.
Okay, and you see here my screen, correct?
Yeah.
And what did you see about the code? The information I just put there.
Oh, I didn't catch it.
Okay, Dylan. Yeah, thank you. Thank you very much, Angel. Thank you. Dylan, can you help, please?
Yes, I'm here.
Okay, can you help me and just let me know if the code would let you use higher values than 0.03 when you have confined concrete?
Well, I would think it'd be too dangerous if the code would just stop at 0.03. It'd be too dangerous.
So is there anything in the code about the use of 0.07 instead of 0.03?
No.
Okay, very good. Thank you. Thank you, Dylan. All right, so just to continue here my questions, I'm going to be asking, How would the code recognize the fact that we have here confined concrete is going to get you higher strengths when you have a spiral columns? I'd like to hear it from Diana.
That would be from the fee factor. So with spiral, we're gonna have a 0.75, and for tights, we'll have 0.65.
Excellent. Very good, Diana. Thank you. All right. So this is what the code says, right? The code says it's going to be only one value, 0.03. Right? We're not going to change here this value for you when you do a design. But what we're going to do, we're going to recognize this fact that you're going to have here higher properties in terms of the strain and the strength. And this is why we're going to give you two items here, two things. The first one is going to be this fee factor, the 0.75 versus 0.65. The other factor, if you look here carefully at this equation, you see it says here 0.8. We're going to increase this factor here for you. Instead of 0.8 and 0.65, now look what happened. It's going to be 0.85 and 0.75. Let me look the old equation. This is going to be here for tight columns. So you see, tight columns and spiral columns, almost the same equation. I mean, this fee factor is going to be now 0.75 instead of 0.65. And look at this equation, 0.85 F prime C AG minus AST plus FY AST, exactly the same thing. But these two numbers, this is 0.8 for the spiral is going to be now 0.85. Instead of the fee factor 0.65 is become 0.75. Now the question is, maybe Desire can help me with this. If you have a column, that has two columns, one of them is tight column, the other one is going to be spiral column. Which one do you think is going to be stronger? If they have exactly the same cross-section area and same reinforcing, vertical reinforcing.
I think the spiral column will be stronger.
Roughly by how much percentage-wise? This is good, Desire, thank you. You answered the question, you can continue or give a chance to someone else.
I'll pass it on.
Okay.
Thank you.
I'm gonna go here with Eddie. Can you help me with this, Eddie? I mean, we understand that spiral column is gonna be stronger. Roughly by how much?
I'm gonna go with about 15%, possibly.
How did you come up with this ratio?
Because the concrete strength or confined concrete is, like you said, it's like 10%, 15%.
Okay. I'd like to hear from Faris. Are you there, Faris?
Yeah, I'm sorry. I'm not really fully paying attention because I'm getting my vaccination.
Okay. All right, Faris.
Sorry about that.
Okay, Faris. No problem. No problem at all. Who else? Abdullah. We have Abdullah? Do we have this? We have Abdullah here? Muhammad Abdullah? Muhammad? Is he gone? Muhammad? He's gone. It's not good. Muhammad. Miguel?
Yeah, Professor?
Yeah. How much is the ratio here between the column axial capacity, if they have both of them, if they have the same concrete strength and concrete cross-section area and the same reinforcement? Which one do you think is going to be stronger? The spiral column, like this guy here, or this one, or the tight column?
I think the spiral column.
By how much percentage-wise?
I'd have to say about like 12%.
How did you come up with this factor, with this ratio?
I got it from the chart on the spiral.
Chart, what chart?
Um, I forgot what the chart is called. Let me check.
Why don't you just look at the screen and answer the question?
Professor, may I volunteer?
Who's this?
Caitlin?
Okay. Go ahead, please. Yes, Caitlin, please.
I thought that the spiral would be stronger by, or it's exactly, I think, 11.75%. What I did, well, actually, I'm not sure if this is the correct method, but what I did was I multiplied 0.85 and 0.75, and I
Yes.
multiplied 0.8 and 0.65, and I just subtracted the difference, which gives you about 12 or 0.12.
So why don't you just take 0.85 times 0.75 divided by 0.8 divided by 0.65?
Oh, yes. Yeah, that was what I did.
And this gives me here 22.5%. You want to try this? Take 0.85 times 0.75 divided by 0.8 divided by 0.65. What I'm saying is, what you can do to find out the ratio is give you 0.85 times 0.75 divided by 0.65 times 0.8. How much is this? 1.22, something like this, right? This means in spiral columns you have 22.6% stronger column. Any questions on this issue about the extra strength that you have in the spiral columns, or we're good?
So if the ratio is over 1.2, then it's stronger as the spiral. Then if it's under, then the other the regular fixed column is better. Then
Okay. Yeah, let me put the previous slide so that we know what we're talking about. You see this equation here? What's the difference between this equation and between the equation that you have here for spiral column? Like you here to look and look at the difference. You see here, this concrete strength is the same, right?
yes.
And Fy times AC is the same. So the difference is going to be phi and this factor. You see this one? Phi and 0.8 versus phi and 0.85. Correct?
Yes.
Correct.
So if I have a column that has the same cross-section area, same steel cross-section area, same steel yield strength, same concrete yield strength, concrete strength at 28 days, the difference is going to be based on this constant multiplied by the phi factor. So this constant by the phi factor is going to be 0.85 times 0.75. On the other hand, on the tight column is going to be 0.8 times 0.65. Now find out the ratio between the two. So it's going to be 0.85 times 0.75 for the spiral column divided by the tight column factors. So in this case, the spiral column is going to be 22.6% stronger than the tight column.
Copy. Okay. Yeah. Now I get it. Thanks.
Okay. So that you have a feeling for which one's going to be stronger and by how much. Are we talking about 2% or 20%? So you have a value of the magnitude. So the same thing also for this spiral column, you're going to have a steel ratio that goes between 1% and 8%. You see this here, right? Exactly the same thing. So when you have a spiral column here, the only difference that we have in the strength equation is going to be these two factors, 0.85, 0.75 versus 0.65 for the phi and 0.8 for this factor. Also, the spiral spacing here is going to be much tighter. It goes here to 3 inches. It says maximum 3 inches. It's not minimum. No, this is going to be the maximum. This is going to be very small. And of course, you have this few values. It says the spiral itself, the spiral size is going to be number 3, right? And it's going to be maximum of number 5. So you can go number 3 or number 4, right? Or number 5. And then the clear spacing should be between 1 inch and 3 inches. the clear spacing. So it's gonna be extremely tight. So if you like here to design the spiral, you can say I'm gonna go here with number 3 at, and then the spacing you say is gonna be equal to 3 inches. It's gonna be spiral. The amount of spiral reinforcement is also given in the code by this equation. Let's look here at these variables and try to understand what is F prime C. Anyone knows F prime C? The meaning of this? Say this is gonna be concrete strength, right? Strength of concrete. What is FYT? It's right there. It's gonna be F sub Y for the spiral itself. AG, total cross-section area of the column. We call this cross-section area of the column. How about ACH? Is gonna be the cross-section area of one core. So now I'm trying to understand, this is gonna be a new thing to me. I didn't hear about this before. Also, I don't understand this row minimum. I mean, is this for the pi? It says for the spiral. And this row S, also I'm trying to understand what is that. It says here volumetric steel ratio. Something new. I understand the steel ratio is going to be equal to cross-section area of the steel divided by cross-section area of the concrete. Definition of a steel ratio. I'm going to say steel ratio, which we usually call it rho, something like that, or just like that, equals AS divided by AG. This is usually the steel ratio. Vertical steel ratio is going to be AS vertical divided by the cross-section area. But here it says rho S minimum is going to be the volume of one spiral in one turn. So we're going to be taking here one complete circle divided by the volume of the concrete within this spacing. So let's say you're going to be taking here a slice of 3 inches. So I'm going to be looking here at the volume of this spiral. And what? I'm going to be cutting here a piece like this. What? Let's cut this piece right here. It's going to be like this. If you take this slice, the height of this slice is going to be equal to the spacing. Let's say to this 3 inches, right? And then within this slice here, you find out the volume of the concrete and the volume of the spiral, and then you find the ratio of the volume of the spiral to the volume of the concrete. And this ratio here, it has a minimum value according to the code. This can be equal to constant AG divided by ACH. And usually this term is going to be more than 1 because you subtract here 1. And then you say here concrete strength divided by FYT. Now a question here too, if I may ask here questions. I'm going to say for 2 Mike. Are you there, Mike?
Yeah, I'm here.
Okay. In the ACI code, do we use F prime C and FYT in PSI or KSI?
PSI.
Okay, thank you. How about here in this equation? Does it matter if I used here KSI or PSI?
I believe you'd want to use PSI if it's a code equation was kind of the advice he gave us, but as long as you're consistent between the two.
Okay, so you should be fine. Here in an equation like this. How about if I have a square root of F prime C? Should I use PSI or KSI?
What was I missed the first part of your question.
If I have here square root of F prime C, so if I have an equation that says F prime C to the power of 0.5. In this case, F prime C, does it have to be in PSI or is it okay to do it in KSI?
Yeah, you would need to do it in PSI.
In PSI.
The same as if you had addition or multiplication within a multiplying factor of the equation.
Okay, thank you. All right, now let me try here to figure out this cross-section area, right? Because this is a thing that I don't know. It says here the core cross-section area. So here is the diameter of the column, and this gives you the spiral. See, it points here to the spiral. So the spiral is going to have this You guys see here, thickness of the spiral is going to be from here to there. And the distance here from the center of the spiral to center of the spiral is called ds. Just the term d refers to the whole distance from here to there. Total diameter of the column, we're going to call it here d, just d. To the outside of the spiral is going to be called DCH. It's going to be for the concrete core. So DCH is going to be from out to out. DS, center of a spiral to center of a spiral. D is going to be the total diameter of the column. Now, we're trying to figure out here, I mean, this is going to be the code minimum value. I understand that. But how about this? How do you figure this out? As I said, we're going to be taking here the volume of one slice of the column and the volume of spiral within that slice. So this is here is going to be the volume of the stirrup itself, or the tire, or not the tire, the spiral. It's going to be equal to the cross-section area of the spiral. Multiplied by pi is going to give you the length, which means the perimeter. Multiplied by ds, it's going to give you what? Pi d is going to be the perimeter times the cross-section area. This is going to be here the volume of the spiral in one round. The volume of the concrete within which you are putting this piece of a spiral is going to be equal to, now it says here the core, right? It's going to be pi times d squared of this dch squared. It's going to be to the outside of the core, times s, which is the vertical spacing between the spiral, divided by 4. This is going to be the cross-section area, pi d squared divided by 4, multiplied by s, which is the height. You can say, where is this at? Yeah, this is going to be s. From here to there is going to be s. So, okay. Also, I have some definition here, the core diameter. ds, the spiral diameter. asp, cross-section area of the spiral rebar. Now, is there a big difference between DCH and between DS? And how much is the difference? You can say here, because look at this equation, maybe I can cross out DS with one of this DCH, right? Because the difference between DCH and DS is going to be very small. We're talking here about number 3. Difference going to be 3/8 inch, 0.375 versus, let's say for a column, it's going to be 16 inch. So it is not really a big deal. These two values are going to be close to each other. So I can reduce this equation a little bit. I can take this ds with this squared, right? And you can cross out the pi and the pi, right? Now let's look how the equation now is going to look like. It's going to be 4asp for the spiral divided by dch divided by s. So we're going to be taking this. So we're going to say ds is going to be very close from dch of the concrete core because there's a very small difference between the two. So now this is going to be the calculated volumetric C ratio. So, okay, let me look at this, try to understand it more. I'm going to go back here to the previous slide and keep this in mind. 4 times the cross-section area for one spiral divided by S times D, CH. Let's say, what happened here if I'm going to be cutting a section this way? Vertical section. DCH is going to be from here to there. So you know what? Let me put the section this way. It's going to be from here to there, right? No, don't worry about D. I don't really need this D. I'm going to say the volume of the concrete is going to be equal to DCH multiplied by the height S, because height S is going to be in that direction. So I'm going to be taking the length from here to there, right? And this spacing is going to be equal to S. This is going to be the cross-section area of the concrete. And how many spiral do I cut through here? I'm going to be cutting through 1 and then 2. So for me, the steer ratio in one direction, you can see here steer ratio in one direction equals 2 ASP for the spiral divided by DCH multiplied by S. And of course, this is going to be divided by both of them, right?
Professor, I'm having a hard time visualize what we're cutting now.
Okay. We're cutting a section through the column this way, looking up. Right? Looking this way. So what do you see when you cut the column section? You're gonna go back here to the previous slide. Here. This is what you see, right? Agree or no? Cutting a section right here, from here to there. Looking up, looking this way. That's what you see. I'm taking a slice here, and the slice is gonna be that big. If I may start right here, I'm gonna say, here's a slice. How big is this cross-section area when you cut through it, right? This is gonna be equals to, if I may write it here, this cross-section area is gonna be D of CH, diameter of this concrete core from the outside of the spiral to outside of the spiral, times S. You know, where's S? S is gonna be the vertical distance from this point to that point. So are you good about this concrete area? Or no?
Yeah. Yes.
Area of concrete equals DCH times AS. How about the spiral reinforcement? How many bars do you think when you cut here through? How many bars you are cutting here through? So I'm cutting 3 2, right? So we're gonna say ASP, area of the spiral, times 2. This is gonna be the steel, right? The cross-section area of the steel. So this is T ratio. In this direction, when you cut the section this way, it's gonna be equal to 2 ASP divided by DCH times S. Does it make sense now?
Yes. Thank you.
I divide the cross-section area of the spiral by this concrete area. Let me take this with me and go to the next slide. Can I put it right here? Can someone help me here and tell me how much is it? I mean, how would you relate this equation to this equation here? Are they exactly the same, or there's a factor or something? I mean, which one's larger, this one or this one?
The original.
This one. It says 4. This one says 2. ASP, ASP, DCHS, DCHS, which means this number here is twice as much as this. So usually they say volumetric steel ratio is going to be equal to the steel ratio in both directions. Not clear. What do you mean in both directions? You can say it meaning, look at this column here. You cut a section this way and then you look that way, right? You figure out rho in this direction, which means this one. And then you come back again and then you cut another section through the column like this guy here. And then you look this way. And then you figure out rho in the, let's say, X direction. So I'm going to be calling this rho Y because the section is going to be looking up. And this is going to be rho X is going to be in the X direction. The steel here is going to be in the X direction. And just add them up to each other. So volumetric steel ratio is going to be equal to rho X. Now where's rho X? This is going to be rho X plus rho Y. So I'm going to say here, rho sub S. I'm going to say here rho S, right? Rho sub S equals rho in the X direction plus rho in the Y direction. Here it is. This one here is rho what? Which one is this one? This is rho X. I have another one, which is very similar to it because the column is symmetrical. So I'm going to say here, this rho Y is going to be equal to the same exact equation. It's going to be rho Y. Now add this to each other. Add this to rho X plus rho Y. It's going to be 2 plus 2 is going to be 4, which means I can say here, rho S, like what I have put there, rho S is going to be equal to rho X plus rho Y. Right? Based on this fact that this is going to be 2 and 2, 2 in each direction of the concrete column, I'm going to have a total of 4 ASP divided by the cross-section area. So rho S, which means a volumetric, is going to be equal to rho X plus rho Y. So it makes sense. Questions?
Yeah, can you explain again why we do it in both directions? I'm having a hard time visualizing when they would be different, like X and Y.
Okay. Here is a column. Which direction is this for the reinforcing? Is this the X direction or Y direction?
The red line is X right now.
The red line. And the steel itself? It's giving the X or on the Y?
When it meets the red line, it's going in the Y.
No. The section is cut in what direction? Does it cut the reinforcing in what direction? The reinforcing is going to be now. You can say now, let me look. All right. Be careful here about my answer. Here's the section that you cut through the reinforcing bars. Am I correct? It's going to be from here to there. Right? You agree?
Yeah.
This cross-section area is exposed in this direction or is getting the X direction? You see, this AS, when you cut the section, look up, right? Look at the elevation. This now reinforcing is in the Y direction.
Yeah.
Because the reinforcing is like this, right? It's coming the Y direction here. AS is giving the Y direction. So I'm going to call this row Y. What is row Y now? It's going to be equal to 2 times the spiral reinforcement. I'm going to say here 2 times the spiral reinforcement divided by area of concrete. Yes? You follow me now?
Yeah.
Okay. Let's cut the same section, but I'm going to be cutting it for the rebar in the X direction. Now, where's the rebar in the X direction? I'm going to say I'm going to have one here and one at the bottom. Now, the rebar is giving the X direction. So I'm going to be calling it row X for this guy here, right? Row X. Yeah, looking. How many spirals do you cut through? I'm going to say 1, 2. How about area of the concrete? I'm going to say area of the concrete, if you cut the section this way, it's going to be the same as area of the concrete if you cut it this way. It's going to be the same as area of the concrete if you cut in any angle, correct?
Yeah.
So all what I need to do is to find out row X and row Y, add them together to get you the volumetric EGCE ratio. Because you see here 2 plus 2 is going to get you 4, which is the same as this equation here. So usually, if you like to find out the volumetric EGCE ratio for a column or any structure, you need to find out row X and row Y, just add them to each other, like according to this equation. Or you can just simply use this equation, if this is okay with you. I mean, if you have it in your notes and you can use it, go ahead and use it, right? There shouldn't be any problem, right? We're good now?
Yeah, thank you.
Okay. So if this is kind of, it's not clear to you, just stay with this equation, you're fine, you're good. I have an example. It says here, P sub U for the column is 540 kips. You have a small eccentricity, meaning that it's okay to use this factor, the 0.85 factor. Check the spiral and use F prime C is going to be 4,000 psi. Fy is going to be 60,000. I have 7 number 8. You see this 7 number 8 is going to be for this rebar, the vertical rebars. And here, we don't really call it 3/8 inch, but this is what you have in the textbook, unfortunately. But this one here is called number 3 rebars. We don't call it 3/8 inch, right? We're going to call it number 3 at 2 inch. Right? We don't really call it 3/8 inch rebar. No one would call it this way. Also, they give you this here 1.5 inch concrete cover. Concrete cover to what? To the outside of the spiral. Meaning, if I'd like you to figure out DCH, I'm going to say DCH equals, it's going to be to the outside of the spiral, it's going to be equal to 15 minus 3 inches. This makes sense? Give it to the outside of the spiral. This is going to be DCH. Now I need to check here the capacity of the column. So let me look here. A gross is going to be pi times 15 squared, the diameter, gross section area, divided by 4. Reinforcing, I have here 7 number 8. You can count them. I have 3 and 3, 6, and here's one is going to be 7.79 for AB. One rebar is going to be 0.79. The steel ratio here, which is cross-section area of the steel divided by cross-section area of the concrete, is going to be 3.1%. This is good, more than 1% and lower than 8%. So here's the first check. The strength, I'm going to be using here a phi factor of 0.75, constant of 0.85, and look at all of these values here. Concrete strength for 176, cross-section area of the concrete. 5.53 is going to be steel cross-section area, the vertical. 60 yield strength, 5 again 0.53 steel area. With that, I have 583 kips as a capacity, more than 540 kips, which is the demand. Demand was given the problem, is given right there. In your project, you need to find out this demand so that you can come up with the steel. And of course, you're going to start here with 1%. If it doesn't work, you add more reinforcing and then find out the strength needed. So done with the slide. Now the last one. How did you hear the spiral? You say the spiral is going to be 12 inch for DCH. We have just done it here, right? Here's DCH, 1.5 inch from each side. Cross-section area of the core. You can find it based on this 12 inches. So it's going to be 113.1. And then use the equation to find out the minimum steel ratio that I can use. The steel ratio is going to be this constant, 0.45. Cross-section area of the steel. Excuse me, cross-section area of the entire concrete column divided by the cross-section area of the core. Subtracting 1. F prime C and FYT, it's okay to use it here in KSI because this is going to give you exact same number as I said. If I said 4,000 divided by 60,000, it's going to be the same answer as if I said 4 divided by 60. But once you see, especially an equation that has square root of F prime C, be careful, you cannot really use KSI. So the steel ratio here is going to be this number here, 0.01. And this is going to be both directions, volumetric steel ratio. The provided, if you recall, I have number 3 at 2 inches. And the steel ratio is given, the calculated one is given by this equation. This is the one I said is going to be equal to rho x plus rho y. So again, if you like to use this equation, you're fine. I'm going to take you back to it. Just use this. Rho s, volumetric steel ratio, based on whatever that you provided, is going to be 4 ASP divided by DCH divided by S. So I'm going to be taking it from there. You say, okay, for APS, number 3, DCH 12 inches, and S, the spacing is going to be 2 inches. So here's what I have provided. In the problem, it says that you're going to have your number 3 at 2 inches, meaning that you're going to have 0.018. Minimum needed is going to be 0.016. So I should be fine because this number is higher than the minimum needed by code. So I should be fine. It says also the clear distance should be ranging from 1 inch to 3 inches. Now the distance here is going to be 2 inches, right? Subtracting 1 bar diameter to find out the clear distance. This is going to be 1 5/8 of an inch. Let me go back here and just double check this. It says here the spacing, clear spacing, right, between the spiral should not exceed 3 inches or less than 1 inch. Clear spacing. What's the clear spacing? From here to there. This is going to be the clear spacing. From this line to this line. When it says here 2 inches, 2 inches going to be from center to center. To get from S, this is going to be S. That's what we call here S. To get from S to the clear spacing, you need to subtract 1/2 of the spiral diameter from here and 1/2 of the spiral diameter, which means it's going to be S minus dB for number 3. This is the reason that in this equation here, if you look at the end, it shows here 2 inches subtracting 3/8 of an inch, which is diameter of the bar. You see here dB. And this is good. I mean, it goes between 1 to 3 inches according to the code, meaning that yes, we're able to do it. Any questions? Any questions? Yes, no?
Can you repeat why does it have to be less than 3 inches again?
Because the code says clear spacing between the spirals must not exceed 3 inches or less than 1 inch. So I'm trying here to satisfy the code requirements, right? Code requirement says the clear spacing between the spiral cannot be less than 1 inch and cannot be more than 3 inches. Okay?
And is that spacing no matter what size rebar it's being used?
Yes, this is
Okay.
correct. Yeah,
Thank you.
regardless of the rebar size. Okay, I'm done for today. I'm going to be going right away to the office hour. I'll see you there. Unless you have a question related to this specific slide set. All right, go ahead and sign out.
Okay, thank you.
Thank you.
Professor,
Yes.
I thought the clear spacing was measured from, like for example, the bottom of one of the spirals to the face of the other.
Yes, this is correct.
Okay. Well, in that case, why do we subtract half of the diameter?
We subtract half the diameter from the top and half the diameter from the bottom. Because S is a clear spacing. So for example, when it says here 2 inch, 2 inches get it from the center of the spiral to the center of the spiral.
Mm.
So you subtract half from the top, half from the bottom, meaning that you subtract 1 bar diameter.
Yeah, that's why I was confused, because I thought that the inside of those 2 inches, there is no bar. Since
I see. Okay.
Professor, I have a question for the office hours.
Yes.
Do you know how long they're gonna take? Because I do have a class at 5:30 Tuesday.
Yeah, I mean, if you are unable, okay, let's say if you're unable to see me, let's say this evening, we can do it later on. Okay?
Later on, does it depend? Like, can I email you a specific time, or do you always have it after this class?
Usually it's gonna be after this class, and if you have any specific time that you're available, try. I may be available.
Okay. I'll email you my availability, and then we can make a time for that.
Okay. All right.
Thank
Very
you
good.
so much.
Thanks.
Have a great
Okay.
day.
Bye.